Welcome back. In the last few classes, we discussed two-dimensional NMR extensively. Especially, we also attempted to interpret COSY, TOXY, coupled and decoupled HSQC, HMPC spectra, and also we looked at homonuclear J-result spectra. Of course, there is no difference between homonuclear and heteronuclear J-result spectra, except the pulse sequence is slightly different. The information content, what you derive, is exactly same because you are going to get the chemical shift information in the direct detection dimension and coupling information in the indirect dimension. Apart from that, there is no difference between homonuclear J-result and heteronuclear J-result spectra. Today, let us discuss something about some of the practical things like whatever you require to know for practical consideration as far as the NMR data acquisition and data processing is concerned. That's what we will discuss today. As far as the practical considerations in getting the NMR spectra are concerned, first we should know about sample preparation, shimming of the magnetic field to get very good homogeneity, calibration of pulses for appropriate degrees. For example, I need 90-degree pulse, 180-degree pulse, or any angle, and also the pulse phases. And I should know about data acquisition, like choosing the appropriate spectral width and designing the number of time domain points, size of the memory for acquisition of the data. These small considerations which are essential, we need to know that. And of course, we have to do Fourier transformation of the data. So we should know how to go ahead in doing these things. These are all essential things, essential practical important points we should know in acquiring the spectrum. I'm talking about one-dimensional spectrum today. Okay, we are not discussing about two-dimensional spectra yet. These are all the considerations for acquisition of one-dimensional spectra. Okay, first thing, what are the requirements for the samples? We need to know how to prepare the sample, what is the quantity of the sample we require, etc. First, as far as the sample quantity requirement is concerned, we require approximately 1 to 5 milligram is reasonable for a small organic molecule, especially for proton NMR. If you want to look for carbon-13 NMR, sample quantity is little bit higher is required because you know the sensitivity of detection of carbon is much less compared to that of proton. So that is what the requirement. Of course, you may say I have synthesized lot of molecule, lot of compound, quantity is very high. I can take more sample so that I can do the experiment faster. No, that is not allowed. Too much of sample sometimes results in broad peaks. You have to take appropriate quantity. Optimum quantity of the sample is required. You can't take too less also because it takes more time for you to get the signal. At the same time, just because you have lot of sample, you cannot take too much of sample also. That gives broad signals. So you have to see optimum quantity, what I have mentioned here. That is, it is only a guideline. Of course, you can decide the way you want. And you have to choose the proper NMR sample tubes. Normally, what is used is 5 millimeter NMR tube. Remember, these are all the things which is shown here. These are 5 NMR tubes. If you have a special probes, you can use 3 millimeter, 1.7 millimeter, and also 1.3 mm tubes. They are available for special probes. Now the sample requirement, if you continue, you need to choose appropriate deuterated solvent. What is that appropriate deuterated solvent? If your sample is soluble in chloroform, you cannot take CHCl3 as a solvent. You always require deuterated solvents in NMR. Like you need CdCl3, dimethyl sulfoxide, CD3CN. If it is a water soluble sample, it is D2O. These are the things you need. Why I require deuterated solvents? It is because I have to use log. What is log? The log is something which I am going to tell you in the next couple of slides. It is to ensure you are going to see that field is not drifting. You know what happens if the field starts drifting? No majority will come in, because every time you send one pulse, you see the samples of the nuclear spins see one magnetic field. Now, if you want the data, you acquire the signal again, once again for co-addition of the data. By then, if the field has drifted, has changed a bit, your resonative frequencies are different. So you will get broad peaks or distorted spectra. You will not get high resolution spectra. Lines are terribly broad, will be terribly broad and distorted. So you need to have a log. For that, you require deuterated solvent, because the log frequency in all the spectrometers is 2H frequency. For example, if you have a 300 megahertz spectrometer, the deuterium resonates there at 42 megahertz approximately. Then your log frequency will be that frequency, 42 megahertz, 42 or 44, whatever it is, you can see the precise value. I'm approximately telling you what I remember. That is very important. And you have to take this sample in the NMR tube, which I showed you, such that the total sample volume or the height of the sample should not exceed 4 or 5 centimeters. Just because you have sample, you cannot fill the entire NMR tube. That's also not good. Too less quantity is also not good. You have to have optimum quantity. This should cover the RF coil area. Taking high amount of sample or less amount of sample, both are disastrous. It gives you distorted peak shapes. So this is very important. The sample height is very important. Remember that. And of course, NMR tube also has to be properly chosen. You cannot take any NMR tube of your choice. But this has been already worked out. Many pioneers in this area have reported what is the optimum choice of the NMR tubes for particular spectrometers or particular frequency of the spectrometers. For example, if you are using, if you have a 400 and 500 megahertz spectrometer, and if you are recording the spectrum in either of them, you have to use Wilmot NMR tubes, whose numbers are some 528 PP7 and Aldrich this number, and Norrell NOR 508 UP7. These are the tubes which you have to use because it is time tested. And the NMR tube could be of borosilicate glass. You also know that. It is a borosilicate glass. Supposing you want to see boron NMR, then you cannot use this. You have to use different type of tube. That is called quartz tube you have to use. And because sample dissolves glass, sometimes you have to use KLF tube. See, these are some of practical difficulties. You will know that later. When you start using the NMR, start using the spectrometer and start recording this spectra, you will have to understand these things. So the proper choice of NMR tubes is essential. You have to use only the identified or those which are prescribed NMR tubes for a particular frequency of the spectrometer. For a particular Larmor frequency, you need to use particular NMR tubes which are prescribed. Okay. When you are making the sample, when you are making the solution by dissolving the sample in the solvent, please ensure there is no turbidity. A turbidity like this will give you bad line shapes. Homogeneity will be destroyed. the B naught field homogeneity will not be very good. This nucleus spins here will not see homogeneous magnetic field. So your line shape will be distorted. You must have a clear solution like this. Very important. You must have a clear solution. And if there are suspended particles which are undissolved, small microscopic particles will be there which are suspended. Please filter them off. Otherwise, that will give rise to magnetic field inhomogeneity. It will destroy the field homogeneity at the site of the nuclear spins. Please remember these are the important points you have to take into consideration. And when you are after doing the sample, you clean the tube. Don't do this at a very high temperature. Don't use microwave oven or oven, and then dry the sample at very high temperature. Sometimes this will warp the tubes. When the tubes are warped, it gives bad spectra. So bad quality NMR tubes gives bad quality signal. So you don't use broken NMR tubes. Sometimes we are used to that. Some tip of the NMR tube, let us say, is broken. We say, okay, no problem. Use the same tube. Sometimes it gives very broad spectrum. If there are broken NMR tubes, please discard them. And temperature fluctuations will be there in the near the sample, in the probe. You have to maintain uniform temperature. If there are temperature fluctuations, that will disturb field homogeneity. So please maintain uniform temperature, for which you have to pass nitrogen gas or compress air always, continuously and uniformly pass nitrogen gas so that you will maintain uniform temperature. That is essential. Other temperature fluctuations or gradients in the temperature will create inhomogeneity and your spectra get distorted. And always when you are doing the experiment, these things will be supplied for you by the vendors. This is called a spinner. This is called a depth gauge. See here marks are given, markings like this. You have to put your sample NMR tube into this spinner, insert the spinner into the depth gauge and make sure the sample is exactly of this height so that your sample is at the center of the RF coil. The markings are given like this. Supposing you put your sample like this, if your NMR tube height is little above, see, it is not exactly at the center of the receiver coil, RF coil. As a consequence, you will get bad signal. Your line shape get distorted. It should be properly positioned like this. You have to adjust the height of the spinner so that NMR tube is properly positioned. Take it out, put it in the magnet along with the spinner, then you'll get a very good spectrum only after making sure it is properly positioned. That is very important. See, improper depth leads to some edge effect called distortion, field distortions because of edge effect. If it is instead of completely within the RF coil, if the, let us say, edge of the sample is at the center, at the edge or in middle of the RF coil, you will get edge effect like this. That gives bad line shapes. Remember, that gives very bad line shapes. So these things, these precautions you must take. Afterwards, you, let us say, you prepare the sample in a deuterated solvent, put it in a magnetic field. What is the next job? You have to lock the signal. I told you locking of the signal is to prevent the drifting of the field. Set it to 2H frequency of your spectrometer. Control the drift, because what happens when the lock frequency is getting changed because of some reason, then there is a compensating current added to the Z0 room temperature shim coil so that it will restore the frequency to the original value. Any field drift is there, compensating field is always supplied by the lock circuit so that the lock will maintain the frequency. That means it will maintain the field and prevent it from drifting. So you will have uniform magnetic field all across the sample volume so that All the nuclear spins will feel the same magnetic field, will sense the same magnetic field, so that there is no distortion of the line shapes, no additional broadening because of field drift. If the field enormously drifts, remember, if the field is drifting more, then what happens is at different times the nuclear spins see different magnetic fields. So the resulting frequency will be different at different times. Microscopically, it may be for a small duration of time of the order of microseconds or milliseconds, but does not matter. That has a devastating effect on your spectrum. So you have to prevent drifting of the field by locking your sample at the deuterium frequency. Very important one. Please remember this. All right. Now let us continue further. Remember, when you are locking the signal, lock amplitude and lock power is very important. These two parameters have to be iterated so that you get a good lock signal, and then after locking you have to ensure signal will not get saturated. Let us say if you have more higher lock amplitude or higher lock power, it may so happen in this region you are saturating. That means your spin population of this deuterium signal are equal. You will not see the signal. So any amount of power if you give or any amount of lock power you give, after some time you will not see signal at all. It gets saturated. So you don't use too much of lock power or don't use too much of lock amplitude. Else signal gets saturated. That's very important. Please remember this. Next, after locking, you have to homogenize the B naught field. This is done by what is called shimming. Means there will be a lot of distortion inherently. There will be inherently inhomogeneities in the magnetic field. And at the site of the nuclear spin, you need to get magnetic field homogeneity of 1 part in 10 to the power of 9 or 1 part in 10 to the power of 10. Very good homogeneity is required. So create a perfectly homogeneous magnetic field over the entire sample volume by what is called shimming. Okay. So what is shimming? It is nothing but adjustment of currents in shim coils until all the inhomogeneities because of field gradients are cancelled out. Then you get a better resolution, and the resolution should be 1 part in 10 to the power of 10. Remember, that is very important. Resolution should be 1 part in 10 to the power of 10. And there are, in all the spectrometers, you have about 24 or sometimes 32 or 36 shim coils. There is shim unit within the magnet. These are called room temperature shim coils. And there are about 36 of them. Some of them will vary the magnetic field gradient along z-axis. By varying the current, you can create counteracting field along z-axis, sometimes along z-square, x and y combination, varieties of things you can see. And each of them here you can see what is going to happen here. If this is the optimum one, where the line shape is very good. If let us say z-square is bad, you can see the shape here. If z to the power of 4 is bad, you can get pedestals like this. Okay. Sometimes x and y can be bad. It is uniformly. You see, this thing is bad. If you are spinning the sample, sometimes you get side bands, first order side bands, like this, second order side bands. These things come because of x squared minus y squared. The second order gradients along x and y will be bad. So varieties of these shim coils will be there. And mind you, getting the homogeneity is not an easy job. You have to iterate upon all of these things. Every time you change these things, you are changing the currents in the shim coils. As a consequence, you are creating the counteracting gradient fields to cancel out the imperfections or inhomogeneities which are inherently present. These are things which you have to practice, and it is not an easy job. And finally, when you are expert, when you do all those manipulations, you will get an extremely good homogeneous field, and lines will be very, very sharp. Not only sharp, the line shape has to be very good. See, it is, remember here, this line shape is very good, but this is not a very good line shape. This is not a very good line shape. So the line has to be perfectly a Lorentzian, start like this, go like this, and then come like this. And I mean, this is not a good shape what I have written. But in principle, you will have to get a very good line shape. And there is a way to test this. You have to test the full width at half height, and then also width at 55% of the height of this, 0.55% of the height of this peak, and 0.11% of the height of this one. So there is a reason for it. I will tell you later. So there is a way to find the line shape, whether it is good or bad. So after doing all those things, you have to use a sample called chloroform, CaCl3, get the proton peak, measure its line width, measure the line width at 0.55% of the height of the signal of this full width at half height, and 0.11% of the full width at half height. Exactly at the center of the peak, you have to measure the line width. That is called full width at half height, and then get the line shape. I'll tell you when we go ahead further. These are some of the useful tips for about shimming. Like see, if Z3, Z4, Z5 odd order gradients are bad, you get like this. Okay, these are all called, these are all called some of the pedestals. See, you feel that some sample is sitting on a pedestal. A signal is sitting on a pedestal like this. This like pedestals. And these are all called sometimes porches, are called verandas. The odd order gradients are bad, like Z square, Z4, and Z6. On either side, maybe on the left side or on the right side, you will get verandas, are also called porches. So these are the things which tells you your shimming is bad. You have to make sure your field homogeneity is very good. Then you must really get a peak like this. Look at the peak here, central peak, exactly at 0. On either side, you have no pedestals, no verandas. The peak should start beautifully like this, go up and come back. You enhance the intensity of the peak very high vertically and measure the full width at half height and find out 0.5%, 55% of this intensity and 0.11% of this intensity. What is the line width? There is a formula how much it should be. It has to have certain specifications, and that specification has to be matched. I hope you are all with me. So shimming is a very, very important point. What happens next is when you are collecting the signal, you have to adjust the receiver gain. Higher the gain, signal intensity will be maximum. And there is a limit for it. You can't keep on raising the receiver gain. When you start doing like this, this is the clipping of the free induction decay. FID gets clipped like this. That is because receiver gain is very high. If you happen to come across such a situation, and if you, without your knowledge, you will enhance the receiver gain and collect the signal, look at it. After doing the Fourier transformation, if you get the spectrum, you will get lots of spikes like this. This is an indication your receiver gain is very high. When you get peaks like this, on either side of the peak, lots of peaks like this comes because of various reasons called sink function. These are all called sink function artifacts, in which case you have to reduce the gain. That is very important. Please remember these points. Next, you have to set the spectral width. You have to choose the proper spectral width. You have to put a carrier offset, and you have to choose the required number of time domain points. You have to calibrate the right pulse width, 90-degree pulse, everything. These are all another thing which you must know how to set these parameters. Spectral width has to be properly chosen. That depends upon your pulse width. Very interesting, right? RF power pulse which you are going to apply for excitation, that decides the pulse width which you have to choose. Remember, the excitation profile is inverse of the pulse width. Let us say you are going to use 10 microsecond pulse width. That is my 90-degree pulse. I'll tell you how to calculate later. If my pulse width, that is 90-degree pulse, is 10 microseconds, inverse of that you calculate in seconds and convert into hertz. This is 100,000 hertz. That means your uniform excitation is decided by profile of the pulse. That means when you do the Fourier transformation of this pulse, you are going to get a sync function. You have to find out where the profile of the that is called the spectral. This is after Fourier transformation, you are going to get this type of this thing. This is what you are going to see, and this is the region where the excitation profile, the power, this thing, this is called power spectrum. This has to be exactly uniform. In the power spectrum, you see, supposing you are going to exit in this region. If you are sitting, your spectral width is like this. In which case, if you sit you have to have a carrier offset, carrier frequency. Your carrier is here and look for 1000 hertz or 5000 hertz, whatever your spectral width here. Then it is not uniform excitation. You will not be even seeing sometimes at this point, you may not even excite the spin. So you have to have a uniform excitation. That is why you have to choose this region. You see? And for a 10 microsecond pulse width, I said here to here is 100,000 hertz. So you have to choose this region. This is the spectral width. This is the region of the spectrum you have to choose. And then excite in this region. So all the spins will be excited with uniform power. The uniform excitation is very important. Supposing you excite in this region, you will not get anything. You will get some signal, of course. I am not saying you will not get completely nothing. But all the spins are not uniformly excited, and the spins are the peaks which are coming in this region may not even get excited at all. So all these things are important points. You have to remember how to choose your spectral width. So that depends upon the pulse width. A 90-degree pulse, which are sharper, let us say width of the pulse is small, the excitation profile is broader. If the width of the pulse is larger, excitation profile becomes smaller and smaller. That means if you want to excite large range of the spectral width, your pulse width has to be narrow. Narrower the pulse width, broader the excitation profile. So let us say my spectral width is 50,000 or more than 100,000. Then you can't take 10 microsecond pulse width. Your pulse width has to be much smaller. Reduce 5 microsecond. If that profile is also not possible, to uniformly excite your spectral width, you have to reduce further. And beyond that, you can't reduce. In which case, you have to move the carrier offset. I'll tell you that as we go ahead. So remember, where do we use soft pulse? What's called selective excitation experiments are there. At which case, in such experiments, we use very soft. This is called soft pulse, broader pulse. So it excites only narrow region. So this is the thing you should remember. The Fourier transformation of a rectangular pulse is a sync function, and this is the point. This is exactly at 1 by t, minus 1 by t, and plus 1 by t. T is the width of the pulse. This defines t. So you have to choose your pulse width such that your excitation profile should, this if it has become larger, this has become smaller. For a pulse width of 5 microsecond, the zero crossings will come at 200 kilohertz. That is 100 kilohertz here. At plus 100 and minus 100 kilohertz, there is a zero crossing. You should avoid that. So you have to choose this only this region. That is the intelligent way of choosing your spectral width. For example, at 400 megahertz, if you want to take 10 ppm is your spectral width, which corresponds to 4000 hertz. So your excitation band should be plus 2000 or minus 2000 from the center of this power spectrum. Okay, from the center of this power spectrum, you should have 2000 here, 2000 here. That's much better. The uniform excitation will be there in that region. So the time it takes to acquire the free induction decay is another point, is called acquisition time. You have to acquire only for the period you have signal. And signals, of course, as you know, I told you, it will decay with time. The FID decays with time because of T2. When does it decay faster? If the signals have the shorter decay time, the signal decays faster. Okay? So you have to acquire the signal, acquire the FID, before the signal dies down. Of course, you can keep on acquiring even after the signal dies down, but then you will have only noise afterwards. So the optimum choosing of the period for which you acquire signal, that the acquisition time is also you have to optimize. You have to properly choose. Supposing you are collecting the signal. This is a free induction decay FID. It is decaying like this, but you are collecting only up to this point. This is called truncation. You have truncated the free induction decay. It is not completely died down. It is coming more towards a rectangular pulse or a square pulse. So what will happen if you Fourier transform this? You get a sinc function like this. Artifacts. So if the FID is truncated, it is not fully allowed to decay. And after Fourier transformation, you get spikes like this on either side of the peak. They're called sinc function artifacts. These are called sinc peaks, sinc function peaks. So FID should not be truncated. You have to ensure it decays completely. Till then, you have to collect the signal. Like this, it has to decay. And also, there is no point. Let's see, your FID has died down somewhere here. You can see very clearly. I'm not a good artist, so I'm not drawing this properly. See, it has died down here. And here, if you acquire signal for a longer time, what is that you are going to get? It is only noise. So that also has to be optimum. You cannot collect the signal only for a short duration so that FID gets truncated. At the same time, you cannot keep on acquiring the signal for a longer time even after the signal died down, because you will be simply picking up the noise. Then your signal to noise ratio will not be very good. It will go down. If you have more noise, your signal to noise ratio will come down.